Hello, everyone. This is the first of my physics videos, and it's intended for students taking Physics 211 at Anne Arundel Community College. Today, we're going to be going through Chapter 6. I've divided the notes on Chapter 6 into 5 parts. This is Part 1, which is an introduction to work, which corresponds to page 1 of your note packet. So today, we're going to talk about, as Rihanna would say, work, 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 which is a very exciting topic. So work, or capital W, is energy transferred to or from an object by means of a force acting on the object. So that can either be, if I'm throwing a ball and I'm transferring energy to that ball, I'm causing the ball to speed up. Alternately, if I'm catching the ball and I'm slowing the ball down, I'm exerting a force on that ball, I'm doing work on that ball, and that sort of work is known as negative work. So it's also important to note that objects can have work done on them. The objects can also do work themselves. So if we talk about work that is done on an object, that would be, say, me throwing a projectile. When that ball is in the air and when it collides with something and it transfers its energy to a wall or to some other ball or something like that, we're referring to work that is being done by the object. So this is something you're going to see quite a lot, the difference between work done on an object and work done by an object. Also important to note that because forces have pairs, work that's being done on an object is being done by an object and vice versa. So as I'm throwing this pen, or as I'm throwing a ball, I am doing work on the pen, and the pen is also doing work on me. I am speeding the pen up, and the pen is slowing my hand down. So again, remember that work happens in pairs, and it's important to think about which object, or whether the object is having work done on it, or whether the object is doing the work. Energy transferred to the object is called positive work. So if you have a speeding projectile and you give that projectile a little push and you make it move more quickly, that is positive work, whereas energy transferred from the object is negative work. So if you're slowing something down, for instance, let's say that there is a shopping cart that's moving towards you, and you push back on that shopping cart and get it to slow down and stop, that is defined as negative work. The work done by a constant force is given by F times S, where S is straight line displacement, and F is the component of force that is parallel to that straight line displacement. Another definition of this is the dot product between the force vector and the displacement vector. Or alternately, if you don't want to think about dot products, you can also think about it as force applied at an angle, or if you have force applied at an angle, work is given by the magnitude of the force vector times the magnitude of the displacement vector times the cosine of phi, which is the angle between them. So let's say that this pen represents the force vector, and this pen represents the displacement vector. Phi is this angle between them. So you multiply the magnitude of this guy, magnitude of that guy, and the cosine of the angle between them, which is phi. All right? Important to note that capital W is work and lowercase w is weight. So weight is still a force. It's a force that sometimes we don't like when we step on our bathroom scales. But work is something which is derived from force, and which is another way of kind of measuring energy. And we're going to be talking about energy in just a little bit. You don't want to confuse the two. Also, we're assuming, for the purposes of this chapter, that the object is particle-like and rigid. So we're assuming that the object behaves as though all of its mass was concentrated in the center of mass. Now, later we're going to run into situations where we can't assume this, or where assuming it might not be a good idea. And we also will run into cases, particularly when we start dealing with collisions, where the objects are somewhat squishy. If you were to crash, say, two pieces of Play-Doh into each other. However, for the purposes of this chapter, we're going to assume that things are particle-like and rigid. All right? The SI units for work are the same as the SI units for energy, and that is the joule. Remember, joule rhymes with cool, and there's nothing cooler than physics and nothing cooler than energy. So the joule is the unit for work and energy. 1 joule is defined as 1 Newton of force times 1 meter of distance. So that's 1 Newton of force across 1 meter of distance. For those of you keeping score at home, you say, okay, well, what if we use the definition of the Newton? And the definition of the Newton is kilograms times meters per second squared, right? So we add in one more distance, and the unit of the joule is 1 kilogram per meter squared per second squared, or 1 kilogram times meter squared over second squared. Rather than using this cumbersome unit, I mean, I'd rather call them joules, but just keep that in mind, particularly if you are doing calculations and seeing what units are dropping out and what units you're left with. This is the unit of the joule, right? Let's go ahead and clear these drawings there. So just to take an example of what positive and negative work look like. So in this first situation, we have a displacement, S, so the object is moving in this direction. We have a force vector, which has a component which is parallel to that displacement vector. In this case, the work is positive, and the object will be speeding up. We are transferring energy from that externally applied force to the object, and that leads to a faster moving object. In this case, we have a force vector which has a component which is anti-parallel to this displacement vector, meaning that the component of F, in this case, the x component, is faced in the opposite direction as this displacement vector. The work in this case is negative, and the object will be slowing down. Let's take a look at a third case where we have a displacement vector this way and a force which is applied orthogonal to this displacement vector. In this case, the work done on the object by this force is 0. So again, you're only interested in forces that have a component which is parallel to the displacement. So only the part of the force that acts parallel to the displacement actually does work. It's also important to note that without displacement, there can be no work. So a case of this would be if you were applying a force to an object which is held in place by the force of static friction. If the force of static friction is not overwhelmed by that externally applied force, then neither the externally applied force nor the force of friction is doing any work. To make things a little bit more complicated, if you have something sliding along and you have a force of friction and an externally applied force, both your externally applied force and that force of friction are doing work. The total work in that case, of course, is governed by the net force, but friction in this case would be doing negative work, and your applied force in this case would be doing positive work. Okay? Let's take a look at the case where work is done by a variable force along a straight path. So let's imagine, for instance, that we have a rocket, and as this rocket is flying through space, the thrust is increasing. Let's say that we're firing our rocket a little bit more as this goes along. So how do you deal with this kind of situation? How do you determine the work? So if we have this example of a graph of force versus position, where position is given on the x-axis and force is given on the y-axis, and as we can see, force is a function of position, the work is going to be the area under the curve. So as this is a calculus-based physics class, whenever you hear the words area under the curve, alarm bells should start jangling in your head and you say, all right, that means I'm going to be taking an integral. So work is defined as the force integrated between these two bounds, x1 and x2, and these again are your limits of integration, x1, x2, and there is your integral. On a graph of force as a function of position, the total work done by the force is represented by the area under the curve between the initial and final positions. So these three statements are basically saying the same thing. We have our graphical representation, we have our calculus representation, and we have that representation in words. Now, for the most part, in this course, we're just going to be assuming that everything is moving in a straight line. But what happens if things move in a curved line? We then need to use something called a line integral, which is explained on pages 185 to 187 of your textbook. And again, this is a misprint. Just to show you how that looks, I'm going to show you the next slide. So let's say that we have a particle that is moving along this curved path from position 1 to position 2. And let's say that we have a force vector which is consistent in both cases. In both cases, the force is pointed this way. The problem that we run into is if we look at an infinitesimally small displacement vector, which is tangent to this curve, there's that calculus again, which we're calling dl in this case, you'll notice that the angle phi in this case is much larger than the angle of phi in this case, meaning that this force in this case is doing less work than the force in this case. This is also somewhat realistic. If you're pushing something at an angle, you'd imagine that the particle is going to be accelerated in this direction as it's an unbalanced force, and that's going to end up, curving your particle over time. How exactly do you deal with that? Well, once again, you take an integral. So work in this case is the force vector dotted with this infinitesimally small displacement vector, which is tangent to the curve, bounded by the positions P1 and P2. So here is your integral. P1, P2, the limits of integration, force vector dotted with dl. Another way that you can think about this is it's the integral between P1 and P2 of the magnitude of this force vector times the cosine of the angle between the force vector and this infinitesimally small displacement vector times the infinitesimally small displacement vector, or the magnitude of the infinitesimally small displacement vector. Or finally, if you're just looking at the component of force which is parallel to this infinitesimally small displacement vector, again, delimited by position 1 and position 2. There's an example of this on pages 185 to 187 of the textbook. I'm not sure how much I'm going to emphasize it, but before it shows up on any quizzes or tests, I'll do a video on just these sorts of line integrals. Now, I might not actually go that particular route. I just wanted to show you what this looks like now, and we may go into detail on it later. Right? So that concludes this particular lecture on work, or this particular segment, and I'm hoping that you'll join me next time when we're going to talk about energy. All right? Thanks very much, and I will see you next time.